Hello everyone, I am Nitish Deshpande at UC San Diego. Today I will share my research on the topic Analysis of Dense Array Massive MIMO with Practical Constraints for the WSA and SSC 2023 conference. This work was in collaboration with Saeed, Jingfeng, and Harish from Nokia Bell Labs, Professor Rodrigo Castellanos from UT Knoxville, and Professor Robert Heath from UC San Diego. I will start by discussing the motivation of our research. With every wireless generation, there is an increase in the number of antennas. There are two ways of increasing the number of antennas in an array. The first approach is to keep the same element spacing and increase the aperture size. However, that approach is not feasible because the array aperture size will increase drastically. The second way is to keep the aperture fixed and decrease the element spacing, which leads to densifying the array. A benefit of densifying arrays is that dense arrays can leverage tight mutual coupling to achieve super-directive gains. For example, when the antenna spacing is less than half wavelength, then the phenomenon of superdirectivity is observed, which leads to very high gains. Theoretically, it can go up to n square gains, where n is the number of antennas. However, is there a catch in achieving superdirectivity? One catch is that achieving superdirectivity requires very high current variation at the antennas. So there can be some hardware bottlenecks. So in this research, we are going to investigate this question of how do the RF components like the power amplifiers and impedance matching networks can limit the superdirective gains in a practical setting. I will first review some prior work on superdirectivity. The main phenomena which enables superdirectivity is the mutual coupling between different antennas. For a typical half-wavelength spaced array, there is no mutual coupling for isotropic antennas. In the absence of mutual coupling, the well-known fact is that the beamforming gain scales linearly with the number of antennas. However, for sub-half wavelength spacing, the mutual coupling is significant, and theoretically it has been proved that with sub-half wavelength spacing, it is possible to achieve superdirective gain, which is quadratic with the number of antennas. Let us look deeper into the different prior work on superdirectivity. Superdirectivity is a very old concept and it has been investigated in the last century. This reference one showed that theoretically it's possible to get quadratic gain when the element spacing tends to 0. However, this is only applicable for isotropic antennas and the gain is observed in the end fire direction. There has been recent interest in superdirective arrays in terms of dipole arrays as well, where references 2 and 3 analyze superdirective gains for more practical arrays. Superdirectivity also has applications like wireless power transfer, which has been investigated using a multi-port circuit theory approach from Tom Mazira's group in NYU. Most of the prior work assumes narrowband circuit models to analyze superdirectivity. There has also been some recent work from Nossek's group in Germany on analyzing dense arrays from a wideband perspective. In this work, we take a more hardware analytical route for analyzing superdirectivity. Specifically, we focus on the different RF components in an RF chain, like the matching network block, which is typically ignored when we consider a block diagram for a MIMO system. We also investigate how the impact of beamforming hardware type influences superdirectivity. So specifically, we are looking at the different power assumptions when analyzing superdirectivity. There can be different kind of power assumptions made for analyzing this gain. So reference one looked only at the fixed power transmitted from the antennas. It did not look at the power which is actually supplied by the radio frequency chains. In our work, we show that the choice of the power constraint can impact or decide what kind of gains you get in superdirectivity. So that's the main focus of this work. And we show that superdirective performance depends on the hardware type and also the power constraint. Let us look at the system model in more detail. To model this dense array massive MIMO, we take a circuit theoretic approach similar to NOSEX work. So each block in the radio frequency chain is modeled as a multi-port network. Let us look at the matching network block, which is modeled as a 2n cross 2n impedance matrix, because there are n input ports from the power amplifier and n output ports at the antenna. The signal from the output of the RF chain, that is after up conversion, is modeled as a voltage source. The current supplied by the power amplifier is denoted by IT, and the current actually entering the antennas is IA. The wireless channel is ZART. We also defined the effective impedance matrix as observed from the ports of the matching network as ZT of F. The end-to-end signal model is expressed in terms of the voltage of the received signal. We can express the voltage of the received signal in terms of the wireless channel impedance vector, the current beamforming vector, the power amplifier, the information symbol, and most importantly, this matrix MT of F, which is dependent on the matching network parameters. MT of F is defined in this equation, which depends on the different block matrices in the matching network and also depends on the array impedance matrix. We can think of this as a transformation matrix which transforms the current from the power amplifier to the current at the antennas through impedance matching. For the case when there is no impedance matching, this matrix will become identity, which means the current supplied by the power amplifier is equals to current entering the antennas. The performance metric that we consider in this work is the signal to noise ratio, which is defined in terms of the wireless channel, the impedance matching transformation matrix, and the current vector from the power amplifier. There are two possible types of power constraints. The first power constraint, as considered from reference 1, is the total power radiated from the antennas, which is expressed in terms of IT, the real part of ZT of F. Whereas when we look at the power supplied from the power amplifiers, we have an additional term in the impedance matrix, which is the source impedance of the power amplifier. Now, the choice of the power constraint will decide the relevance of the matching network, as we see in the following slide. The objective function is the SNR, but there can be two different optimization problems depending on the choice of the power constraint. For the first power constraint as considered from reference 1 is the TRP constraint, which applies an upper bound on the total radiated power. Whereas the power constraint that we propose to use for analyzing this work is the power supplied from the power amplifiers, which includes this additional term from the source impedance of the power amplifier. We see that after solving this problem P0, the optimal SNR obtained depends only on the wireless channel and the impedance matrix of the array. It does not depend on the matching network. So under this power constraint, although this expression is optimal, it does not give any insight into the dependence on the matching network. Whereas including this power constraint, which is the total supplied power constraint from the power amplifier, gives insight into the dependence of the matching network on the SNR. As you can see, this is captured through the matrix MT, which is the transformation impedance matrix. So the problem P1 is more practical formulation to analyze the super-directive gains because it also captures the dependence on the matching network. Finally, we also look at the impact of the choice of the beamforming architecture. So we consider three different architectures. The first one is the fully digital architecture, in which we can independently control the magnitude and phase for each element across different frequencies. So this is a frequency selective hardware. So the beamforming capability is maximum for the fully digital architecture. Second architecture is analog true time delay, where we cannot control the magnitude of each element, but we can control the phase for different frequencies. And the third architecture is the analog phased array, where we can only control the phase for a fixed frequency. As we see, the number of constraints increase in the optimization problem as we move from P1 to P2 to P3. I will now discuss the simulation setup and provide some design guidelines from our simulations. In our simulations, we look at a uniform planar array consisting of half-wavelength dipoles. The spacing between the elements on the x-axis is dx and in the y-axis is dy. The receiver is assumed to be in the far field. The array impedance matrix is dependent on the ideal impedance matrix obtained from using closed form expressions from the Balanis textbook that is derived using the induced EMF method. And then we also look at a loss term to model the practical aspect of the dipole antennas. The wireless signal is assumed to be line of sight, where we have the array steering vector dependent on the frequency and the frequency dependent path loss, which captures the antenna radiation pattern for the dipole antennas given by this expression. Finally, for the matching network, we assume a simple conjugate matching technique given by this expression. So this is the multiport matching technique obtained from reference one. But reference one was limited only to look at the center frequency, whereas we look at the frequency selectivity model for this matching network. So for this, we assume a simple pi topology, where in this pi topology, we have these admittances, which can either be inductor or capacitor, depending on the value of these parameters gamma. So once we choose the capacitor and inductor value, then we can get a frequency selective response from this pi topology architecture. Let us look at the received SNR as function of the number of transmit antennas on the x-axis for a fixed aperture size at center frequency 5.5 gigahertz. Since the aperture is fixed, as the number of elements on the x-axis increases, the array density increases in this direction. We see that there is a sudden jump in the received SNR beyond 14 antennas, which means as the element spacing decreases below half wavelength, the superdirectivity effect starts to kick in. However, as the element spacing is below 0.35 lambda, we see that the gain starts to saturate. Further, this plot is the same irrespective of whether we have matching or don't have matching, because the received SNR is plotted under total rated power constraint, which is the problem P0. But we can see the difference in the maximum to minimum current magnitude ratio, which we plot in this plot. So the blue curve shows the ratio between the max to min current at the antennas, and the red curve shows the ratio of max to min current at the power amplifier. From this plot, we see that there is a high current variation at this point where we see the superdirective effect. However, at the power amplifier, the current variation is less, which means that the matching network kind of acts as a shield to the power amplifier to avoid high current variation, which is very useful from a practical perspective. Now we look at the received SNR under the total supplied PA power constraint, which is the problem P1. For the narrowband case, we see that for the multiport matching technique, we observe the superdirective effect beyond 14 antennas, which is same as the previous plot. However, when we look at no matching case, we see that the superdirectivity effect has reduced, which shows the importance of matching for the narrowband case. However, for the wideband case, when we look at the received SNR at 5.45 gigahertz, when the matching is designed for 5.5 gigahertz, we see that when we consider the multi-port matching with the frequency selective model, the beamforming gain starts to decrease for the frequency which is offset from the center frequency. So this plot shows that we should avoid using multi-port conjugate matching for wideband system. In our future work, we will propose a more sophisticated technique where we optimize the data rate and get a good matching network. Finally, we look at the performance of different beamforming architectures. As expected, the fully regional architecture performs the best among all the three architectures. We also observe that in terms of the frequency response, available bandwidth decreases as the flexibility of frequency-related beamforming decreases. We also see that the no matching case is performing better for the wideband as expected, because when the frequency selectivity of conjugate matching starts to kick in, then there is a huge performance degradation for frequencies offset from the center frequency. I will now summarize the key takeaways from this work. In our work, we showed that the total supplied PA power constraint is more practical because it unravels the relevance of the impedance matching at the transmitter. We also showed that the multiport matching helps to achieve superdirective gains for moderately dense arrays and only narrowband systems. For future work, we propose to optimize the impedance matching networks with a wideband objective like achievable rate and also incorporating the Bode-Fano matching constraints. It's possible to leverage the mutual coupling in dense arrays to achieve super bandwidths. So this work was limited only to a MISO system, and it's open direction to extend this to SIMO and MIMO systems. Thank you, and I look forward to your questions and comments.